Before watching this lecture, you should have an understanding of the log-log model and why the beta parameters are elasticities. The log-linear model is another very popular model in econometrics, perhaps not as popular as the log-log model, but still used quite a lot. So remember, the log-log model is based on the power function, f of x, a times x to the c. Starting with the power function, we could step by step develop the log-log model for econometric analysis. The log, actually, let's write that down, that leads to the log-log model. The log-linear model starts with not the power function, but the exponential function. If you remember, the exponential function looks like this. It's a constant times and reverse thing. We do x in the exponent instead. This is an exponential function. One exponential function is particularly important, and that's the natural exponential function. So if we write it as a times e to the x, that is, we pick this c to be precisely e, the natural 2.71 something, then it's the natural. If we add one more parameter to the natural exponential function, that will make it more flexible. So if we add a parameter b here, then it will be able to capture a lot more possible data sets. So just a quick reminder of what the exponential function looks like. For example, for a equal to 0 and b equal to 1, it is the natural exponential function, e to the x. If you do, this is a1 and b1. I might have said a0, but I meant a1. If you do a equal to 1 and b equal to minus 1, it looks like this. So this is a1 and b equal to minus 1. And you can also stretch it. For example, this one would have a equal to, goes through here, maybe 1/2, and b maybe 1/2, at least less than 1. So this will be nice. It can capture, maybe if our data looks something like that, it can capture that data. So the exponential function with this extra parameter will lead to the log-linear model. Let's see how. So what we do is we simply assume that the expected value of yi given xi is this power function. We change the parameters to beta. That's the econometrics way of doing it. And then we write it as e to the beta to xi, which we sometimes write instead as exp beta to xi. That might be a little bit more convenient. So x parenthesis and e raised to something is exactly the same thing. We make it into econometrics by adding a multiplicative error term, just like in the log-log model. So our complete specification is this one, at least for the case with one explanatory variable. That's the complete specification. And just like the log-log model, epsilon I is then the ratio of yi to the expected value of yi given xi. If we have more than one explanatory variable, we would write it like this, still as a product. So beta 1 e to the beta 2 xi2 times e to the beta 3 xi3. But remember the power rules, we can also write this as beta 1 e to the beta 2 xi2 plus beta 3 xi3. And in this case, we get just so many superscript and subscript that we tend to prefer the exp notation. Beta 2 xi2 plus beta 3 xi3. So the part in here will be a linear function. Again, this formulation is not a regression model. A regression model needs to have an additive error term, but we can easily make it into a regression model, and we need to add one more ln rule, log rule from the log lecture, and that's the following. The logarithm of e to whatever, any function, is f of x. So log e to anything is that anything. Apply that to our model. We see that we get log yi. It's a product of three terms, this term, this term, and this term. So we just take the log of each term and sum them. So log beta 1 plus, I'm not sure if I should write it down, let's not. So the second term would be log of e of this. So log and e just cancel each other out, and we're left with beta 2 xi plus log epsilon I. Final step, we make this little trick. We call this beta 1 prime. We call this epsilon I prime. These are my new error terms, and we have the log linear model. Log yi is beta 1 prime plus beta 2 xi plus epsilon I prime. You can also see why it's called log linear. That's because we have a log here, and this is linear. So the log linear model. Let's generalize this to a case where we have an arbitrary number of explanatory variables. So the general setting of the log linear model is this one. The expected value of y given xi is beta 1 times e to the, and then the all these terms, beta 2 xi plus and so on. We have an error term, which is the ratio of yi to the expected value of yi. Multiply both sides of this by the expected value of yi conditional on xi, and we have the complete model. So this is our DGP, our data generating process. Can't do much about this one. Don't really have any way of estimating parameters of such a model, but we can fix that by logging both sides. So if we log both sides, we get this result. Log yi, log beta 1 plus a linear function plus log epsilon I, which we prefer to write like this. Log linear model. So the next question is then, how do we estimate this model? Well, that's actually easier than estimating the log model, because now we only have to transform the y data, the dependent variable. So going back to Gretel, if I want to estimate my final, have final as my dependent variable in a log linear model, I need to use log of final as my dependent variable, but I should not log the x variables. Those should be as they are, like this. Now it's a log linear model. Estimates, and we need to interpret these ones. Again, this model is not linear in data, although it may seem like it's linear in data because we have this xi's are sort of not with powers or anything like that. I have log y on the left hand side, so the actual expression of y is something which is not linear. Beta 2, for example, it's not the derivative of y with respect to x2. It's the derivative of log y with respect to x2, and that's not the same thing. Neither can we interpret these as how many percent will y increase if x increases by 1%, as in the log-log model. What we will see is that the interpretation is different, and it is as follows. This number right here, 0.014, for example, it answers the following question. If SAT-M increases by 1 unit, that is, you get one more point on your SAT-M score, then the expected result on the final exam will increase by 0.014 or 0.14%. So for example, if the final result is 100 and SAT-M increases by 1 unit, then we expect the final result to go up by 0.14% or 0.14 points. And that's the interpretation of these parameters. Increase x by 1 unit and y increases by, take this coefficient, multiply it by 100 and say this is how many percent y will increase. So let's try to figure out why we have this interpretation of beta. Let's use the simple function to begin with. Y is equal to sum a e to the b times x. The percentage change in y is delta y over y, the change in y over the starting value of y. So that's the change, that's the percentage change in y. Now let's take that divided by x, which is the change in x in units, not percent. So let's look at the percentage change in y over the change in x, not the percentage change in x, but the actual change in x in units. I can write this as delta y over delta x times 1 over y. And this is approximately dy dx, the derivative, times 1 over y. So this expression is the percentage change in y if x increases by 1 unit. If this is 1, then this expression reverts to the percentage change in y. So let's evaluate this for the exponential function. So dy dx is equal to a times the derivative of the exponential function. This comes in front, e to the bx, and dy dx times 1 over y is ab e to the bx over a e to the bx. This cancels, and so redoing this after the crash, these cancels, and I'm just left with b. So we see that this parameter here is indeed a measure of the percentage increase in y when x increases by 1 unit, at least approximately so. Taking that to the linear regression model, the expected value of y given x is this power function, this exponential function, beta 1 e to the beta 2 x, and by exactly the same arguments, beta 2 is the derivative of ey given x with respect to x times 1 over y. Not y, of course. Y in this example is the expected value of y. Again, just like in the log-log model, there's an alternative way of looking at this. If I take log of both sides, I have log expected value y given x is log beta 1 plus beta 2x. So we can see that this beta 2 is simply the derivative of log e y given x with respect to x, not the log x as in the log-log model. So an alternative interpretation of the parameter beta 2 is how much does the log of the expected value of y increases when x increases by 1 unit. Generalizing this whole thing, we were here concluding that it's a linear model in parameters but not in data. And so the interpretation of the parameters are then as follows. The beta j parameters for j going from 2 to k is either the derivative of log expected y derivative of x, or the derivative of the expected y derivative of x times 1 over expected value of y. In any case, the important part to remember is that it measures the percentage change in y when x increases by 1 unit. And to get the correct interpretation of beta j, you take the estimated value bj multiplied by 100. If that comes out to be, after multiplying by 100, comes out to be say 0.03, then you can conclude that an increase in x by 1 unit increases y by 3%. So we have this multiplied by 100, and we have the percentage increase in the expected y if we increase this particular x variable by 1 unit while keeping the other explanatory variables constant.